For the next keynote, I'd like to welcome on stage Wasiq Bokhari. She's the chairman of Pasqal's board, and he will invite us on a trip to the future of quantum. Please, ladies and gentlemen, welcome Wasiq.
So the topic of my talk is very bold, charting the future, the course for quantum innovation. You know, Yogi Berra has this saying, it's very hard to make predictions, especially about the future. So I'm going to set the stage up front in terms of how accurate my predictions are going to be. Most of my career has been about building new technologies and scaling them at some of the largest technology companies in the world. And I'm also a big student of the history of technology development and innovation. So to look into the future, I will start off by looking in the past, and then we'll see how it goes. So in our talk today, first I'll talk a bit about the brief history of high-performance computing. And then I'll talk a bit about what we are seeing in Gen AI, what are some of the key lessons, constraints, opportunities, and so on. And then finally, how do we go from there? So that's my talk. And you'll probably see a lot of parallels here in terms of what we see today in quantum computing and what we saw in supercomputing when it started. The very first supercomputers that could fill a room, they were highly proprietary systems, and they had very few users. Government agencies, very wealthy companies, and so on and so forth, were very technical problems that could be solved. So because of the proprietary and expensive nature, the usage was small, and our metrics for measuring the value were also very technical. We're looking at flops, floating point operations per second, and so on. It sounds kind of familiar where we are in terms of the quantum space today. At some point, though, it became very evident to people that, look, we cannot persist in this state because the utility of this resource is much larger, and therefore it should be shared more broadly. At that point, there was a realization that instead of proprietary few systems, we could create clusters of systems, which are lower in cost, but we can network them, we can connect them. And by doing so, we can get effectively the same performance. There are some trade-offs. You can get the same performance, but at a very much lowered cost. And by doing that, we were forced to invent communication protocols like InfiniBand, which could allow jobs to be interspersed between different computers across a cluster without sacrificing performance. But it lowered the barrier to entry, opened the market even more, and more importantly, it opened our minds to think about what kind of applications and problems we could solve with those. It was no longer the domain of the very few. Notice the similarities. There was a very consequential announcement that was made just earlier today. So we are seeing some patterns repeat over time. What happens then? Now when you can distribute these jobs and they can run in a parallel fashion, the constraint starts to become more on the software side. So how do you batch these jobs? How do you send them to different places? How do you break them up? So you can, and then how do you put them back together so that you can get same effective results? So now hardware, system level innovations and design decisions are driving software, and how that software will drive again back the hardware and the system level. So we had to invent new sort of protocols or extend existing old protocols to meet this challenge. And the other thing that changed was, remember we started off with flops. Now all of a sudden we are thinking about broader applications, and these are specific applications. So the old benchmarks don't work. Now we have to think about a different way of measuring the utility and the value, even though it's a technical metric. How do we do that for each specific application? The industry evolves again. Now, in the background of all of this, we start to see new components arise. GPUs come, FPGAs come. These are very application-specific components that add to CPUs. Now think about the QPUs that we talk about as another addition into this mix. and how this will affect the rest of the ecosystem. But once you have very specific pieces of hardware that work with CPUs, now you can create very application-specific workloads. And by making application-specific workloads, you start an entirely new cycle, entirely new flywheel of the kind of value you can deliver. And this starts, again, having a backward effect in terms of how we think of system design, system integration, the software, and so on and so forth. So the cycle continues, but one is driving the next. And then we come to the rise of the cloud. We take it for granted. And Amazon was one of the inventors, actually, of cloud computing. But the core idea behind the cloud was twofold. Number one, for a customer, they should only be able to make a business decision in terms of the storage or compute or anything else, any other resource they need. They shouldn't have to do that themselves. So you lower the barrier to entry. The second is the customer should be completely abstracted from the details of the technicals behind it. I shouldn't have to make a decision about what system to make. I just need a resource. You combine those two, you get immense scale. And even though initially it was a lot about storage and compute for technical, perhaps very arcane uses, now cloud-based systems are everywhere. It's part of every consumer offering. And that has completely blown the market open. Just Amazon itself, AWS, it does $500 billion in revenue just from its cloud computing division with very healthy margins. So these are just some of the items that I was looking at as I was trying to think about what happens when quantum computers come into the mix. These are 3 points that I think are pretty interesting. Maybe they're relevant to how the quantum space will evolve. First is, we saw monolithic proprietary systems become off-the-shelf, distributed, heterogeneous. Big game changer. Second, once these systems became established, we could think about new applications and new use cases for it. And that drove the entire system-level design cycle again. And the movement from on-prem to cloud, it just reduced the barrier to entry. And these are exactly the dynamics that we are seeing today as quantum computing enters the space of general-purpose, high-performance computing. Now, there are multiple challenges. I think speakers before, they talked about these challenges, but I see them being very relevant as quantum computing becomes part of the mainstream. Benchmarking is something we talked about. Currently, we still talk about specific technical metrics, number of qubits, and so on, and that's entirely relevant. But at some point, perhaps, we will think about very application-specific architectures, and we will ask the question, for this particular drug discovery problem, which uses this graph-based method, what is the right benchmark? And then of the 4 primitives that Loic mentioned earlier, we can have similar benchmarks that we think about. And in the end, that's the only thing that's relevant. The other things don't matter. Because then I can take that as a part of a utility or a resource that's available to me as a business, and I can make my ROI analysis. That's one place where we need to go. The second is, our tool ecosystem is very artisanal. It's few people here, few people there, maybe they're here, maybe not, they're not here tomorrow. At some point, we have to find a way to make it more robust and make it more standardized. So we have some foundation that we can build on. By the way, none of this is new. This has all happened before. So in a sense, history is repeating itself, but perhaps we can learn from it. Data. Data is the big moat and the big challenge. It's real data and synthetic data, data security, and how do you integrate data. That is something, right now we're not thinking about it, but very soon when quantum computing is part of mainstream, we'll be exposed to mountains and mountains of data. And some of them would be very, very sensitive data. That's one item I think will apply to us in terms of challenges. And last, George talked about this earlier, this is part of the DNA of the company. Data centers currently consume as much energy as small countries. that is not sustainable. So if we have any hope of using Gen AI to solve our climate change problem, that is not a very smart way of doing it. But by coming up with new architectures that fundamentally break the limit or the constraints of old architectures, that is one of the big promises of quantum computing. And it can actually be utilized to redesign some of our classical computing systems as well. Now let me talk about Gen AI for a second. It is a hot topic. But earlier, one of the panelists said something brilliant, which is that new technologies are exponentials, and we don't really see them until it's too late. So the Transformer paper came out in 2017, and nobody paid attention to it. And when GPT-1 was launched, it really didn't do anything interesting. But people didn't give up. They kept training it with more and more data. In fact, that was one of the hypotheses, was to throw more data and see what happens. And all of a sudden, new, unexpected, emergent behavior came out of that language model. That was GPT-2. The rest is history. And this is another thing that we will continue to see in the Gen AI space. First of all, if we look at the various vectors in terms of hardware development, software development, access to data, if we just do a 10x on each and every one of those, we are seeing a 1000x improvement over what we have today in, I would say, roughly 5 years or less. Some would argue that number is going to be 10,000x. Second, we currently think that a lot of these LLMs are not good at complex reasoning, but that is also being addressed. In fact, we are seeing systems which are perhaps, some of them are based on knowledge graphs, which are exhibiting pretty robust reasoning, and it will get better. So this will coexist with quantum computing, and it is not either or, it is and that's something we have to think about as we think about the future. On the opportunity side, I think this represents a few things. There is a lot of language data, but is there enough physics and chemistry and biology data, especially synthetic data? I think that's a very interesting opportunity for us. The second is, I don't know how many people have been keeping up with agent-based systems. So this, as a different kind of paradigm or application of large language models, it shows yet another kind of complex behavior that we did not expect from straight LLMs. These things will proliferate. And if you assume that LLMs, especially the open source LLMs that exist today, they will run natively on your devices, will have a cloud component, and they have an agentic basis, this becomes a really interesting triad of computation that is available to us. And of course, the big holy grail here is some sort of recursive self-improvement, which will lead to what people say super intelligent AI and so on. Whether it's malevolent or not, that's a separate topic. So where does it leave us? Going from proprietary and closed to open and heterogeneous seems like a winning bet, and that is the bet that we have taken at Pasqal in terms of standardizing so we can scale. Offering complete systems, we talked about one of the announcements today, but there's much more to be done. There's much that is unknown. And this is one of the challenges always in these inflection or these highly scaling curves is it's actually very tough to predict what the needs would be. Hybrid systems we talked about, data we talked about, and code design is a very important part. We are early, but if we start working backwards from specific workloads and ask the question, how should we design not only the software but the hardware that is specific for those workloads, that will serve us well. It has served HPC really well. So I feel that has a part in the future for quantum computing. We know all the application areas. The most interesting one is the very last one to me, the unexpected areas. When the cloud computing divisions, AWS was being started at Amazon, the initial vision was very small. It was just to consume data, store and consume data for Amazon's internal e-commerce uses, and so on and so forth. It has completely changed. It looks nothing like the original S3 service. Same thing will happen in quantum if we can reduce the barriers to entry. So how do we do that? So suppose you're a company and you're wrestling with, is quantum too early? Is it too late? Is it not ready? Is it not ready? One of the biggest things that I've learned in innovation, in bringing innovation to market and scale, is we have to start treating the new innovations as adults and not assume that they are kids and not ready. Let us start asking the question, what is a real important problem for us as a business? Let's challenge the business. Because we have very smart, motivated people working on this. And we figure out a way to break that problem into step-by-step pieces, and let's go solve them. That is how every industry has progressed. And that is the opportunity ahead for us. So I would encourage everyone to have courage, step in, and let's see how we can solve these problems. So with that, key takeaways, evolution of QC systems to distributed. I believe quantum computing is the third pillar. And finally, it is all about collaboration and creating value together. So with that, thank you very much.